Next, we come to perhaps the most important concept in chemical equilibrium. This concept was given to the chemistry world by a person called as Le Chatelier and is named after him. This concept is called Le Chatelier's Principle. It states that if a chemical reaction at equilibrium is subjected to a change in pressure or concentration or temperature, then the equilibrium shifts in the direction so as to minimize or counteract the change. This concept has tremendous applications in various scenarios. For example, pressure may increase or decrease, volume may increase or decrease. You may add some extra gas in the equation. You can change some concentration factors. You can add a catalyst in the reaction. All of these things will have an implication so as to follow the Le Chatelier's principle, wherein the equilibrium will shift so as to minimize or counteract to the change. Note that in all of these reactions, as far as the temperature is constant, Kp or Kc remains constant. This is a very important thing to be remembered from a Le Chatelier's principle as well. Now, how do I remember Le Chatelier's principle? Well, there is a very simple way to actually remember Le Chatelier's principle. The simple way to remember Le Chatelier's principle is by actually remembering the example of a spring. Now let us say that this is a spring, right? What happens with a spring? The more you compress and then leave that spring alone, with greater force does it try and come back to its equilibrium position, right? So essentially, spring is a system wherein the more you try and change it, that much more force will it come back to its original position. Le Chatelier's principle related to equilibrium is sort of similar in that context, wherein the more you try and change a particular equation, the reaction will go in the direction so as to counteract the change or minimize the change. Now that we have learnt Le Chatelier's principle, let us understand the implications of Le Chatelier's principle. Firstly, let us learn how does Le Chatelier's principle affect the direction of a reaction when it comes to constant temperature. In this, let us take first case as delta n equal to 0. So what is the typical example of delta n equal to 0? Let's take the formation of hydrogen iodide. Let us, for clarity of concept, assume that there are initially 1 mole and 1 mole of hydrogen and iodine. Now at equilibrium, if we assume 2x moles of hydrogen iodide to be formed, then 1 minus x moles of hydrogen will remain. Similarly, 1 minus x moles of iodine will remain as well. So in terms of concentration, molar concentration, we have 1 minus x by v, 1 minus x by v and 2x by v. Now I had introduced the concept called as degree of dissociation. Now degree of dissociation is basically the amount of substance that has been dissociated divided by original substance. So in this case, degree of dissociation alpha is equal to the amount of substance that has been dissociated is x divided by original substance is 1. So which is equal to x. So x is equal to alpha. So I would be using alpha in these equations going ahead. So therefore, if we define Kc is equal to 2 alpha by v the whole squared divided by 1 minus alpha by v into 1 minus alpha by v, which comes to, therefore Kc is equal to 2 alpha the whole squared divided by 1 minus alpha the whole squared. Now, in this case, if volume is increased, so initially let's assume that volume is 1 liter. Now 1 liter becomes 2 liters or 5 liters or 10 liters. What will be the impact on the reaction? Well, the answer to this is very simple. Given that Kc does not have any volume term remaining, even if you increase your volume by 2 from 1 liter to 2 liters or 5 liters or 10 liters, or you decrease your volume to half a liter, 1/4 a liter, there is no effect on the reaction. Kc is unchanged and alpha also is unchanged. Now, if alpha is unchanged, then there is no impact of volume change on this reaction. Now, if you assume that PV is a constant, if volume change does not impact the reaction, then even pressure change does not impact the reaction too. So even if pressure is increased on this kind of a reaction, there is no impact with respect to the extent or direction of the reaction. Let us understand the implications of Le Chatelier's principle. Now initially, let us take a look at constant temperature where delta N is equal to 0. So now let us assume that initially there are 1 moles of hydrogen and 1 moles of iodine. Then at equilibrium, we will have 1 minus x and 2x moles of hydrogen iodide. Now their molar concentrations are 1 minus x by V, assuming V liters of container. 1 minus x by V, 1 minus x by V and 2x by V. Now we have already defined degree of dissociation alpha to be the amount of substance dissociated divided by the original amount of substance. So in this case, that is equal to x by 1 in case of hydrogen. So hence, I will be using alpha in place of x. So now Kc at equilibrium is equal to 2 alpha by V the whole square divided by 1 minus alpha by V into 1 minus alpha by V. So hence, in the Kc equation, there is no volume. Okay. So now the question is, if volume is increased, what is the impact on the reaction? Now at a constant temperature, Kc is constant. So if volume is increased, is there any impact on the reaction? Because there is no volume term in the Kc, we can safely assume that even if the volume is increased or volume is decreased, it will have no impact on the reaction. Alpha will remain unchanged. So if alpha is unchanged, then there is basically no impact on the reaction. Now, similarly, if PV is equal to nRT and that is considered to be constant because temperature is constant in this case, we can safely assume that even if pressure changes in these reactions, even then there is no impact on the extent of the reaction, because delta N is equal to 0 and there is no presence of volume term in the Kc. Let us look at the case where delta N is less than 0. In this case, delta N is minus 2, the formation of ammonia example. Now, in this case, let us assume initially there are 1 moles of nitrogen and 3 moles of hydrogen available. Now, at equilibrium, if we assume 2x moles of ammonia to be formed, then we will have 1 minus x moles of nitrogen remaining and 3 minus 3x moles of hydrogen remaining. In terms of molar concentrations, we will have 1 minus x by v, 3 into 1 minus x by v and 2x by v as their molar concentrations. Now, Kc is defined as molar concentration of ammonia the whole square divided by 1 minus x by v into 3 into 1 minus x by v the whole cube. So in this case, in Kc, if you look at it, it will be 2x the whole square into v square divided by 1 minus x into 3 into 1 minus x the whole cube, which comes to 2x the whole square divided by 1 minus x the whole raised to 4 into v square into 3. So now in this case, if you look at it, in the Kc term, there is a v component there. Okay. So now what will happen if volume is increased? In terms of alpha, we can also write this as 2 alpha the whole square divided by 3 into 1 minus alpha the whole raised to 4 into v square. Why? Because degree of dissociation is equal to alpha x when we have taken 1 moles and 3 moles. Great. So now if volume is increased, what will happen? For volume is increased, Kc will remain constant because it is constant temperature. So the alpha will have to counteract and reduce. Now if alpha has reduced, it means that degree of dissociation has reduced. If degree of dissociation has reduced, then we will have the reaction going in the backward direction. Got it? Now, if volume has increased, conversely we can say that pressure has decreased too. So if pressure decreases, even then we can say that the reaction goes in the backward direction. Now let's take the reverse case. If volume decreases or pressure increases, let's examine what happens to the reaction. Now see, clearly Kc is constant at a given temperature. So to counteract the reduction in volume, what will happen is alpha will have to increase. If alpha increases, then the reaction goes in the forward direction. So in this case, where delta N is less than 0, if volume increases, then the reaction goes in the backward direction. If volume reduces, then the reaction goes in the forward direction. Next, let us learn what happens with respect to Le Chatelier's principle, where delta N is greater than 0. So let's take your favorite example, dissociation of PCl5, phosphorus pentachloride. In this case, let us assume that there is 1 mole of PCl5 initially. At equilibrium, it will be x moles of PCl3, x moles of Cl2 and 1 minus x moles of PCl5. So in terms of molar concentrations, again since alpha is equal to x by 1, I can use alpha and x interchangeably. We'll get 1 minus alpha by V, alpha by V and alpha by V as the molar concentrations. So now Kc is equal to alpha by V into alpha by V divided by 1 minus alpha by V. So therefore Kc is equal to alpha square divided by 1 minus alpha into V. So therefore Kc is and V are inversely proportional. So now in this case, if volume increases, let's examine what happens. If volume increases or conversely pressure decreases, let's examine what happens. If volume increases, since Kc is constant, your denominator has increased, so alpha will have to increase as well. So therefore alpha increases. Now if alpha has increased, then the degree of dissociation has increased. Degree of dissociation has increased, meaning that the reaction will proceed in the forward direction. So clearly, if volume has increased or pressure has decreased, the reaction will move in the forward direction for delta n greater than 0. Now let us look at the opposite case. If volume decreases or pressure increases. Now since Kc is constant, now in this case what has happened is volume has decreased, so alpha also has to decrease. Now degree of dissociation has decreased. Now if degree of dissociation has decreased, then the reaction will proceed in the backward direction. Got it? So this is the impact of delta n greater than 0 and the impact of increasing pressure or volume. Let us understand the application of Chateliers principle if an inert gas is added to the reaction. Now, what is the implication of inert gas addition to the reaction? Essentially, in a gaseous reaction, you are adding some more volume, some more moles of an inert gas. Case 1, let us study the impact of addition of inert gas at constant volume. So now at constant volume, essentially, if you look at the gas law, PV is equal to nRT, right? Now in this case, P by N is equal to RT by V. So now assuming temperature is constant, volume is constant, and R is obviously a constant, these all things become a constant in itself. For a reaction like AA plus BB giving CC plus DD, we have Kp is equal to partial pressure of C, the whole raised to C, into partial pressure of D, the whole raised to D, divided by partial pressure of B, the whole raised to B, into partial pressure of A, the whole raised to A, right? So now this is actually equal to, if Nt is the total number of moles, Na is equal to number of moles of A. Similarly, Nb, Nc, and D are number of moles of B, C, D. Then you will have Kp is equal to Nc by Nt, the whole raised to C, into P raised to C, into Nd by Nt, the whole raised to D, into P raised to D, divided by Na by Nt, the whole raised to C, into P raised to A, into Nb by Nt, the whole raised to B, into P raised to B. Now in this case, essentially what I've done is, I expressed partial pressures using mole fraction and total pressure. So now in this case, what happens is, this is equal to Nc raised to C into Nd raised to D, divided by Na raised to A into Nb raised to B, into pressure by Nt, the whole raised to delta N, where delta N is equal to C plus D minus A plus B. Got it? So now here what I have done is, I have expressed Kp in terms of number of moles of ABCD and total number of moles and pressure, total pressure. Great. So now in this case, assuming volume is constant, we have P by Nt is also equal to constant by gas law. We have looked at this piece over here, right? So now in this case, when inert gas is added, Nt increases. However, Kp is constant at a given temperature. Given that other things are constant, Na, Nb, Nc, Na, Nb, Nc, Nd are all constants, and Kp is also constant, so pressure will increase, but no impact on direction on reaction. So even if volume at constant volume and addition of inert gas, even if delta N is greater than 0, equal to 0 or less than 0, there will be no impact on the direction of the reaction. What will just happen is that the pressure will increase or decrease so as to counterbalance the delta Nt. Hence, whatever be the delta N, be it greater than 0, equal to 0 or less than 0, on addition of inert gas, basically there will be no impact on the direction of the reaction. The reaction will neither go forward nor go backwards, but the pressure will increase to counterbalance the increase in total number of moles. Now, let us understand what happens when, in Le Chatelier's principle, we look at addition of inert gas at a constant pressure. Now, from the previous derivation, we have derived Kp in relation to pressure. Let's use that here again. Now we have pressure as constant. So now when inert gas is added, NT increases. Now let us examine the different cases. So case 1 where delta N is equal to 0. Now if delta N is equal to 0, then what happens is Kp is basically equal to Nd raised to D into Nc raised to C divided by Nb raised to B and Na raised to A, the whole into 1, because delta N is equal to 0. So hence, when delta N is equal to 0, addition of inert gas will not change the direction of equilibrium of the reaction. Next, let us look at delta N less than 0 at constant pressure. So now in delta N less than 0 at constant pressure, we have Kp is equal to Nd raised to D into Nc raised to C divided by Nb raised to B into Na raised to A, the whole thing, into P by Nt, the whole raised to delta N. Now when delta N is less than 0, we have this to be less than 0. When inert gas added, Nt increases, therefore P by Nt reduces. Now P by Nt, the whole raised to negative something, will effectively increase. Now if this is increasing, then since Kp is constant, we have Nd raised to D into Nc raised to C divided by Nb raised to B into Na raised to A. This whole term has to reduce. Now this can reduce only if the numerator reduces or denominator increases. So effectively in both cases reaction goes backwards, in backward direction. So effectively at constant pressure, if delta N is less than 0, then when inert gas is added, reaction goes backwards. Just to reiterate, at constant pressure, if delta N is less than 0 and inert gas is added, then the reaction goes in the backward direction. Why? Because in order to counterbalance the increase in P by Nt, the whole raised to something negative, you will have to have this thing happening. Next, let us discuss the case where del N is greater than 0. So now, again taking back from the reaction, Kp is equal to Nd raised to D into Nc raised to C divided by Nb raised to B into Na raised to A, the whole into pressure by Nt, the whole raised to delta N. Now when inert gas is added, Nt increases, number of moles increases. So therefore P by Nt, because pressure is constant, reduces. Now since delta N is positive, we have P by Nt, the whole raised to delta N, also reducing. Now because this term reduces and we have Kp as constant, Kp at a particular temperature, at constant temperature is constant, hence we should have Nd raised to D into Nc raised to C divided by Nb raised to B into Na raised to A. This term should collectively increase. Now this term can increase either by increasing the numerator or decreasing the denominator. So in both cases, essentially, products are increasing, reactants are decreasing. Hence, the reaction is going in the forward direction. To summarize, when delta N is greater than 0, at constant pressure, if you add an inert gas, then the reaction proceeds in the forward direction. Just to summarize again, the effect of addition of inert gas at constant pressure. If delta N is equal to 0, there is no impact. If delta N is less than 0, the reaction goes backwards. If delta N is greater than 0, then the reaction goes forward. This is your summary. Summary for adding inert gas at constant pressure. Next, let us study within Chateliers Principle the effect of changing temperature. There was a scientist called Van 't Hoff who actually studied this particular phenomenon and derived a relationship between the entities when temperature is changing. Essentially, what is the impact on equilibrium constant? So now he derived his equation is now called as Van 't Hoff equation. Van 't Hoff equation states that log of Kp2 by Kp1 is equal to delta H0 divided by 2.303 R into T2 minus T1 divided by T1 T2. In this case, delta H is the heat of reaction. Kp2 is the equilibrium constant at temperature T2 and Kp1 is the equilibrium constant at temperature T1. Great. So now let us study what are the implications of Van 't Hoff reaction. So let's take the first case where the reaction is endothermic. If reaction is endothermic, then delta H is greater than 0. In this case, if temperature increases, then let us study what happens. If temperature is increasing, then T2 minus T1 is greater than 0, right? So now what is happening is delta H is positive, 2.303 R is also positive, T2 minus T1 divided by T1 T2 is also positive. So hence the entire term is positive and we have Kp2 is greater than Kp1. Next, let us study the next case, which is the reaction is exothermic. Now in this case, if the reaction is exothermic, then delta H is less than 0. If delta H is less than 0, and let's now examine if temperature is increasing. So T2 minus T1 is greater than 0. Now in this case, delta H is negative, 2.303 R is positive, T2 minus T1 by T1 T2 is positive. So we will have this whole term to be negative. So therefore, log of Kp2 by Kp1 is negative. So therefore, Kp2 will have to be lower than Kp1. Now let us look at another problem. Bromine gives 2Br. The equilibrium constants at 327 degrees and 527 degrees are 6.12 into 1 into 10 raised to minus 12 and 1 into 10 raised to minus 7. Now clearly, as temperature is increasing, the K is increasing as well, right? 10 raised to minus 12 is going to 10 raised to minus 7. So now the question is, what is the nature of reaction? For this, what is the logical thing to do? Well, the logical thing to do is actually to visit the Van 't Hoff formula, because there are essentially two K's involved over here, right? It is actually quite a straightforward question. However, if you get confused between what to apply over here, then you may get, wavered answers. So now this is the Van 't Hoff equation. Now here, what is happening is K2 by K1 and effectively its log is going to be positive. T2 minus T1 by T1 T2 is also positive. So clearly, for this side to be positive, even delta H has to be positive. If delta H is positive, it means reaction is endothermic, right? So this is the way in which you interpret problems and solve them in such a way that it becomes very logical. Next, we should understand one particular concept that is there in both equilibrium and thermodynamics. We need to understand the relationship between the equilibrium constant and standard free energy. Now, the relationship between this is delta G is equal to delta G naught plus RT ln Q. In this case, delta G naught is basically the standard free energy change for a reaction which would accompany the complete conversion of all reactants at standard conditions to all products at standard conditions, which is 1 molar or 1 atmosphere. Now, when it comes to an equilibrium state, what we have is, at equilibrium, the standard free energy change delta G is equal to 0, and at equilibrium Q, which is the reaction quotient, is equal to K. So therefore 0 is equal to delta G naught plus RT ln K. So therefore delta G naught at equilibrium is equal to minus 2.303 RT log of K. This is a very important reaction in context of equilibrium as well as thermodynamics, and this equation is called as the Gibbs free energy equation. Guys, now let's take a tougher problem. So now the question is, we have the following data wherein hydrogen reactions are there. There are some two reactions with K1 and K2 that are indicated at 2000 degree Kelvin. Now we have to find out the K for essentially we have to answer whether this third reaction is endothermic or exothermic, right? So now for doing that, what is the logical thing to be done? In this, what is required is, we will need to find out the relationship between Kp at 2000 degrees and Kp at 1000 degree Kelvin, and then say whether delta H is positive or negative to find out whether reaction is endothermic or exothermic. Perfect. So now for finding K at 2000 Kelvin, first of all, I will use these two data points that I have and manage to get this reaction, right? So for that, what I did was I multiplied the first equation by 2 and found out the K1 dash to be 4.4 into 10 raised to 2. Next, when I added this equation to 2, this plus this, then I get this equation effectively, and the effective K3 is 4.4 into 5.3 into 10 raised to 10 power 10. Okay, K3 is basically K1 dash into K2. Okay, now the actual reaction K3, K which we want, is the reciprocal of this, because this reaction when mirrored becomes this. So the third reaction Kp at 2000 Kelvin is equal to this, which comes to 9.7 into 10 to 10 power 7. This is at 2000 Kelvin, mind you. Now we know that K at 1000 Kelvin is 2.24 into 10 power 22. So clearly K has reduced as temperature is increased. Now we apply this concept in Van 't Hoff. In Van 't Hoff, what is happening is Kp2 by Kp1 is negative, so this piece is LHS is negative. T2 minus T1 by T1 T2 is positive because temperature is increased. So delta H has to be negative. Now given that delta H is negative, this reaction is exothermic, right? So essentially what we did was, we found out the relationship between the two equilibrium constants at different temperatures, and then applied that in the Van 't Hoff formula to find out the reaction is endothermic or exothermic.